if we consider Earth and we consider the satellite orbiting around Earth in a circular motion, then we know its force is going to be given by G, mass of Earth, mass of satellite over the radius squared, the distance from the center of Earth. And because it's going in rotational motion, its acceleration is going to be v squared over r. So if we use Newton's second law that says F equals ma, then we get G, mass of Earth, mass of satellite over r squared is going to equal the mass of the object times v squared over r. And that leads us to the velocity of the satellite that it's orbiting is going to be G, mass of Earth, over its distance, square root. Now, since there's the radius of the Earth plus how high above the Earth's surface, we can say that r, let's say this is r above, and r would be the radius of the Earth plus how far above it is. So this is 6.37 times 10 to the 6 meters plus it's 300 kilometers above, so that's 3.00 times 10 to the 5th meters. And if we add these two, we get 6.67 times 10 to the 6th meters. So now the velocity in part A, or the speed, if you wish, is going to be the square root of 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared times the mass of the Earth, which is 5.98 10 to the 24th kilogram, all over 6.67. Keep in mind that this is still under the radical time, 10 to the 6 meters. And if we do this, we get about 77.30 meters per second. To find the period is denoted by capital T. It's the distance this satellite travels, which is one circumference of the orbit, divided by the speed. So this is 2 pi times 6.67 10 to the 6 meters over 77.30 meters per second, which gives us about 54.20 seconds, or approximately 90.4 minutes. And its acceleration radially is v squared over r, as we said. So this is going to be 77.30 meters per second quantity squared over 6.67 times 10 to the 6 meters, which gives us an acceleration of 8.96 meters per second squared. In part B, we're asked for the work to get the satellite in orbit. the energy associated with a satellite in orbit can be given by the potential energy, G, mass of Earth, mass of satellite, over 2R. It's half of the potential energy, if you think about it. And this is minus 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. Mass of the Earth again, 5.98, 10 to the 24th kilogram. The satellite is 1,000 kilograms, over twice the radius of the orbit. And this gives us negative 2.98, 10 to the 10th joules. And this is to get it to the final location is this far. The satellite's kinetic energy is 0 on the launch pod, so at the launch there's only negative kinetic potential energy, which is G, mass of Earth, mass of object over the radius of the Earth. Plug in these numbers in, we get minus 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, 5.98, 10 to the 24th kilogram, still 1,000 kilograms, but now this is just 6.37 times 10 to the 6 meters. And this gives us a potential energy of negative 6.25 times 10 to the 10th joules. So the required work, if you remember, the work is the change in potential energy. So this is going to be E2 minus E1. And if we do that, we use these numbers, we get about 3.27 10 to the 10th joules. So part C, we're asked how much additional work would have to be done to make the satellite escape the Earth. We saw that the initial kinetic energy for a space shuttle E2 was negative 2.98 times 10 to the 10th joules. So that's the minimum required mechanical energy to put it in orbit. So to increase this to an amount of 0, we would have to require the opposite amount, which is since E2 is negative 2.98 times 10 to the 10th joules, which is to put this in orbit, to escape Earth's atmosphere, would require W to equal minus E2, which is 2.98 10 to the positive 10th joule.